All right. Here's what we're going to do. I'm going to go ahead and pick it up with the next section in the book, the next section of learning on the covalent and the nonpolar and polar covalent bonds. And what I'm going to do is go through this content and then go back to the on your owns. What the plan would be is if there's any time at the end and you understand the three-dimensional Vesper geometries and you don't want to stay to go through the on your owns, I'll allow you to go at that point. But again, I'm not promising we'll even get that far. We need to cover this content today. Okay? So we'll cover and this is not real deep and complex, but if people have trouble with it, we're going to stay here for a while and make sure we understand this concept of the polar and nonpolar covalent bonds. Now these PowerPoints, I haven't used them before, so I put them together to try to explain these concepts, you know, from the book and in a way that I think makes sense, but you know, occasionally I'll put a slide up there that I think makes perfect sense, and this is the feedback I get from you. So what I think is, say, hey, this is going to make it crystal clear. It's obviously not crystal clear, and so that's when I do my little juggling act up here, trying to say, okay, well, let's draw something on the board and let's go. So we'll see how this goes today. So nonpolar covalent and polar covalent. The last, in addition to, they use the phrase polar covalent and purely covalent. And I mentioned last year when I taught this course that whenever I see the word purely covalent, I think nonpolar. And now, since I taught it last year, every time I see nonpolar, I think purely. So basically, we're going to talk about bonds that are either polarized or are not polarized. Okay? They're either going to be a nonpolar or polar. They're either going to be polar or purely covalent. Those two terms are used interchangeably by a lot of people. So nonpolar is the same as purely covalent, and polar covalent is the other type. So we're dealing with covalent bonds. Now, in a covalent bond, we're at the place now we understand that a covalent bond means that we're sharing an electron, that each element has at least one electron in the game of sharing here, and so they both have an invested interest in staying around, so they get to sometimes share the other atom's electron, so they complete their valence shell, right? So this bar indicates a shared pair of electrons. And sometimes one of those electrons is at one side, and sometimes the electron is at another side. In fact, if we remember that, if we indicate this, and now we're at the place where we can see, okay, this is a shared pair, this is a bond. It may be referred to as a physical bond, but remember, it's not really physical. They're not really touching each other, but the atoms aren't going to simply separate without a lot of energy being placed in there to separate them. That pair is actually, remember, is just this shared pair of electrons. Now, this is where y'all go, ooh, ah, I think, if I remember, because I did this a week and a half ago. But I think my next click does something. We said these two electrons are actually being shared, right? And this is also the point where I'm going to show something using the PowerPoint, the ability of the PowerPoint that's not, there goes the big red head in front of the camera. Don't worry, it'll come back again. Go ahead. Go ahead. Okay, so I'm going to show you something that's not technically accurate, but I think helps communicate the point. Remember before we said you have to learn the Bohr model of the atom before you can learn the quantum mechanical model? You've got to learn it with a center and rings of orbits. Even though we know that's not exactly how we currently understand the atom, that's the way we're going to show it first so that you can understand some certain things, and then I'll say, okay, based on that, kind of partially wipe your mind of that, and now let's talk about the S and the P and the Ds and the Fs and all that kind of stuff. I'm going to show you something up here using the PowerPoint, which is not technically the way it works, but I think it communicates this idea of sharing and equal or unequal sharing. All right? So, you know, if, say, describe how this works, and you were to describe how the PowerPoint's going to show it to you, it's not technically correct, but the concept is there. The concept is right. So we've got two electrons that are being shared between these two chlorines. We've got one electron being shared, okay? Again, this is not technically the way it works, but this gives you the idea. We've got an electron being shared. So I want you to see that, hey, this electron is at sometimes in the domain of one chlorine, and at other times in the domain of the other chlorine, okay? So that's what's happening here. An electron is actually being shared. But it's not a shared electron, right? It's a shared electron pair. Okay? So here's the idea. These two electrons that are being shared by these two chlorines are being shared between the chlorines. And sometimes there's one at one chlorine and one at the other chlorine. Sometimes they're actually both at one side and they're both on the other side. But the bigger principle we want to get here is that they're being shared between the two atoms. That's why you say sometimes this chlorine, it thinks both of them belong to it, and occasionally they're not home. And this chlorine thinks, hey, they both belong to me, but occasionally they're not home. Where are they? They're over at the neighbors. Okay, but they still count them towards their octet. So these two electrons here, this is the PowerPoint way of showing these two are being shared. But I want you to notice something. How are they being shared? And when we talk about polar and nonpolar, in the case of this is a nonpolar covalent representation. We've got two chlorines. We've got a homonuclear diatomic molecule here. Two chlorines. Now let me ask you a question. What is the force that we talked about before that an atom uses to try to possess an electron? The force it uses to try to gain an electron. Good. Electronegativity. Electronegativity is the amount of force that the atom uses to get an electron. And what we're seeing here, and the reason why they're being shared and why they're staying close to these is because both of the chlorines are exerting a force to possess the electron, an electronegativity. They're both exerting force on that electron. Now, in the case of a homonuclear diatomic, you've got two chlorines. Ask you the question, which chlorine is exerting more force? Or is a chlorine exerting more force? Which one of these two atoms has a higher electronegativity? They don't. They're the same. Chlorine and chlorine, they both have the same exact electronegativity. Because they both have exactly the same electronegativity, they both exert exactly the same amount of force on the shared electrons. And because they both exert the same exact amount of force on the shared electrons, the electrons are around each of the chlorine atoms in the same amount of time. There's just as much probability that I'm going to find one or two electrons, whatever I'm looking for, at one chlorine as it is that I'm going to find it at the other chlorine. They're equally shared. Last year I used the example. Let's say that two of you went out and you purchased an automobile together. You say, here's the deal. We're going to both chip in. We're going to put our money together. We're going to buy a car. Okay? And that car is going to be at my house. You know, we started with the example, my house 1 week, your house, or my house one night, your house the next night, but then you end up running back and forth all the time, right? Say, tell you what. It's going to be at your house a week. It's going to be at my house a week. It's going to be at your house a week. It's going to be at my house a week. And we set up a relationship where we both are peers. We both have the same amount of force on one another, the same amount of influence. We both have a desire to have the car, but we're willing to share. And so in order to have a car, we go together on it. We share it equally. That's one situation. And that's what's being presented here. These two chlorines have teamed up, and they're equally sharing these two electrons because they both want two, but they only have one. So in order to get another, they share it. And because they're both exerting the same exact amount of force, they get the electron the same amount of time. Does that make sense? But some bobbles, yes or no? If you really don't get it, I need to see that. But just the concept. These are these two atoms here are exerting the same amount of force to get the electron, so therefore they get it the same amount of time. Now that idea right there is the nonpolar bond. What does that mean? That means at any given time, the charge of this molecule is still going to be, it's going to be neutral, right? Because it's a neutral element, excuse me, it's a neutral molecule. But we're going to start looking at within the molecule, is there a plus side and minus side of the molecule? And because the electrons are equally shared between both sides of this molecule, between the two atoms, we would say that it doesn't have a charge across the molecule. It's equally shared. So that's a nonpolar covalent bond. It's covalent because it's a shared. If it weren't covalent, it would be ionic, and it doesn't apply because ionic electrons are not shared. Ionic electrons, the bond is formed because the electrons are given away and taken, and then the opposite charges attract. Covalent bonds are because the atoms decide to share. And they're sharing in a nonpolar way. They're sharing equally. Each atom gets the electron an equal share as its partner. Well, there's another, actually more common type of bond. Oh, here's the definition for you from the book. A nonpolar covalent bond is a covalent bond, it means it's shared electrons, in which the electrons are shared equally between the atoms involved. Equal sharing of electrons means it's a nonpolar covalent bond. Different situation. We have an HCl molecule, hydrogen chloride, hydrochloric acid. Okay? Again, representing a shared pair with hydrogen. Its octet rule is complete. It's satisfied because it's only looking for 2, and it has both of its electrons in its shared pair. And chlorine, which is a 7A element, so it has its 6 plus 1 gives it 7, and then the other shared from hydrogen fills its octet. So this is our HCl molecule. Now, question is, we're going to show, sorry, wrong way. Again, the shared pair is actually 2 electrons that are being shared between the 2. Let me ask you a question. Which of these 2 elements has a higher electronegativity? Now remember the trend on the chart. Electronegativity, its trend is from lower left to upper right. Everything, the ionization potential or ionization energy, the electronegativity is from bottom left to top right increasing. Radius is from top right to bottom left increasing. So we're talking about a trend that's increasing in this direction. Now look at the periodic table. You've got hydrogen over here, and you have chlorine all the way over here in 7. Now based on up and down, hydrogen would appear to have a higher electronegativity because it's higher, but chlorine is much farther to the right. And so when you assess that, yeah, hydrogen's a little up, but chlorine's a whole lot to the right. We'd say that chlorine has a higher electronegativity. Translating that, the chlorine is exerting more force to get an electron than hydrogen is. Okay? The chlorine is giving more energy in the effort to gain an electron than hydrogen is. They both want an electron. We're not talking about it wants more so it's going to steal it. They're still going to keep sharing, but they're going to share in a little different way. Hydrogen's going to share its electron. And again, technically this is not correct because there's no way to show this with the abilities of PowerPoint right now without creating custom animation. But what I'm trying to show here is that hydrogen is sharing its electron, and so is chlorine. But because chlorine is exerting so much more force, I needed a way to show that chlorine has more electrons around it in time than hydrogen does. This never gives you an example when hydrogen has both of them, and that does happen. But the only thing this animation is trying to demonstrate is that typically as you look at the molecule, you will tend to find at least one, if not both, of the electrons around the chlorine. Okay? Now, does this animation show you that? It gives you the idea that, hey, the only thing it doesn't show is occasionally there's 2 at hydrogen, but what it's showing you now is there's always at least 1 at chlorine, and sometimes there's 2 at chlorine. I'm just trying to show you an imbalance, that the electrons are imbalanced towards chlorine. What's happening here with our car analogy? Okay? You and your friend, you go out and buy a car, and you say, okay, we're going to share this thing, and your friend says, yeah, I'm going to have it a month, and then you can have it a week, and then I'm going to have it a month, and you can have it a week. You say, hey, that's not fair. They say, hey, that's a deal. Or they're just bigger and say, shut up, or I'm not going to give it to you at all. Right? They're bullies. They're exerting more force on it than you are. They have more influence than you do, so guess what? They get the car more days than you do. They still kind of throw you a bone once in a while, let you have it, but you can have it every other week. But and you can't have it on weekends. I get it Friday through Sunday every week, and then I get it 3 weeks out of every month. Now they're exerting even more force. In the analogy, they're exerting even more electronegativity towards that car, which is the shared electron. Okay. So again, in this situation, what we're trying to demonstrate is that chlorine is the bully. Chlorine has a higher electronegativity, and so even though they're sharing the pair, chlorine is going to keep them as much as it can, more often. It's going to hold on to them. It's going to get it more often. And that idea of where do the electrons reside more often? Hopefully you'd be able to look at this and say, hey, between hydrogen and chlorine, the electrons reside more often at chlorine than they do at hydrogen. Why? Because chlorine has a higher electronegativity. It's exerting more force. Okay. So now we get into this concept here of the polar covalent. The polar covalent bond is a covalent bond in which the electrons are shared unequally between the atoms involved. There's an unequal sharing taking place. Yes, ma'am?
It's about the nonpolar bonds. You said that the atoms have the same amount of force.
Same electronegativity. Mm-hmm.
So do the atoms have to be the same?
Yes. Yes, we're going to get to that. But that's right. That's technically true. In order for it to be a perfect, here's where it's kind of nuanced. In order for it to be a perfectly nonpolar bond, they have to be two of the same element. Because every element has its own unique electronegativity. However, like a lot of things, since the only way it's actually going to be perfect is if it's a homonuclear diatomic. But other than that, in chemistry, when you get more into this concept, they have different levels where they say if the difference between the electronegativities is less than 0.3, then it's purely covalent or nonpolar. If the electronegativities are between 0.3 and I believe it's 0.5, then it would be a polar covalent. And if it's above 0.5, it's going to move up to 1. And if the difference is 1, it's ionic. That's part of the math part of it. I don't think we go into that in this course. But right now we're just dealing with the concept. So yes, technically speaking, the only way there can be a perfectly purely covalent or perfectly nonpolar covalent bond is if it's between two identical atoms. And I think that's the way we're going to run with it in this class. If it's not between two identicals, it's going to be polar to some degree. But the difference is technically a range. So you don't have to be actually the same and be considered nonpolar if you're doing a math-based electronegativity differential. For this class, I'm pretty sure we're going to stick with, if they're not the same, it's going to be polar. So polar covalent, shared electrons. Electrons are not shared equally. And we get into this concept of partials. A new sign for you. Partials. This is a symbol for partial charges. And what we're showing here is as we look at the molecule and kind of consider it, let's say this is two-dimensional here, this way, and we're looking at the center of the atom, the center of the molecule, that it's not perfect, the same on both sides. There's a difference, right? This side of the molecule, on your right-hand side as you look at the slide, tends to have the electron more often, and because it tends to have the electron more often, within the molecule, it tends to have a more negative charge than the other side. Why? This other side occasionally has both electrons over here, but on the whole, on the average, it sees the electron less. And because it sees it less, it's relatively positive compared to the other side, which tends to be more negative. And so the symbol just means partial. It's partial positive and partial negative. Now, if I'm looking at the entire molecule, if I'm outside of the molecule looking in, do I see a charge? Is there a charge for the HCl molecule? No. From the outside looking in, there's no charge for the molecule as a whole. However, I do note that one side tends towards a negative and one side tends towards a positive, but they balance each other out in terms of the entire molecule. Okay, so that's how that works. So this is polar covalent, meaning it's shared electron. One side tends to be a little more negative, one side tends to be more positive. The side that tends to be negative is the side that gets the electron more frequently, and the side that gets the electron more frequently is the side with the higher electronegativity. Then we add another symbol to our Lewis diagrams as well. Because this side tends towards positive and this side tends towards negative, we're going to draw an arrow above the bond pointing in the direction of the negative. And we do that because we're also going to add the next symbol, excuse me, we're going to add the next symbol of a slash on the side that's a positive. So consider this the plus side. You make an arrow pointing towards the negative and you put the positive slash for the positive side. And so what you're indicating there is, hey, this is my Lewis structure, and I recognize that it's a it's a polar covalent bond. The electrons favor this direction, which makes this side positive. So if you had this and this given to you, you should be able to draw that arrow and put the plus on the plus side. So point towards the negative, positive on the positive side. Or, given the arrow, you should be able to fill in the, hey, this is the partially positive side, this is the partially negative side of the molecule. Okay? So the arrow points to the negative and puts the plus slash on the positive side. So the example in the book says, identify and label the polar bonds in an ammonia molecule, should say. Okay? So first we're going to draw the Lewis structure. The Lewis structure looks like this. We have nitrogen, NH3. Nitrogen is a 5A element, so we knew we had 2 plus singles, and hydrogen forming covalent bonds around it. Then identify the bonded atoms. They're going to be hydrogen and nitrogen, and that's it, right? The only bonds we have in this molecule are hydrogen and nitrogen, hydrogen and nitrogen, hydrogen and nitrogen. That's the only bond sets we have. So we identified the bonded atoms, the bond sets. Third, determine the greatest electronegativity. Yes. So which of those two elements has the higher electronegativity? Right, I would agree with nitrogen. Nitrogen is far to the right in column 5. Hydrogen is only one energy level higher, so the farther to the right outweighs the one up. And so we end up with nitrogen having a higher electronegativity. Since nitrogen has a higher electronegativity, what is my indicator going to look like? Where's it going to go? It's going to point towards which side? Hydrogen or nitrogen? It's going to point towards the nitrogen because the nitrogen is partially negative because it has the higher electronegativity. And so we're going to annotate that on the bond symbols by giving it this symbol right here. So I know when I go back to my Lewis, and later when I go back to my Vesper, I'm going to replace whatever I see here as a single covalent bond, or maybe even a double covalent bond, but I'm going to add to that this symbology right here. So there we have our Lewis. I'm going to go ahead and add those indicators, the arrows and the plus signs, orienting the positive end towards every hydrogen and the negative arrowhead side towards the nitrogens. Questions on that? Yes, sir.
So what does those symbols mean?
Which one? This one here?
Yes, sir.
Or this means partial positive. So within the molecule, this side of this bond tends towards positive. Means it tends not to have the electron. This side is partial negative, meaning that this element has a higher electronegativity, and it tends to have the electron. So remember, we're talking about a negative charge. If it tends to have the negative, it becomes more negative. If it tends not to have it, it becomes more positive. And this arrow plus sign symbol combination points to the negative and indicates the positive. We just take that and add that to our two-dimensional Lewis structure.
So that'll be answers to the questions like this?
Identify and label the polar bonds. It would look like that. So you have to have a good Lewis structure first, and then add on top of that your polar symbology. a C2F4 molecule. So C2F4, we're going to draw the Lewis structure. Starting with the Lewis structure, then identify the different bonded atoms. So what are the bond sets we have? We have a carbon to carbon, and we have a fluoride or fluorine to carbon. Are there any other bonded combinations in there? Can you see of any other atoms that are bonded to other atoms other than a carbon to carbon and a fluorine to carbon? No. Okay. We're going to go through and determine the greatest electronegativity. Let's look at each of the bond sets. Carbon to carbon. Equal electronegativity. So it's going to be a nonpolar bond between the carbons. But in fluorine to carbon, you look at the chart, fluorine is to the right of carbon. Fluorine has a higher electronegativity than carbon. So the fluorine, because it has a higher electronegativity, is going to tend to possess the electron more frequently. Because it has it more frequently, it's going to become a partial negative. As it becomes a partial negative, it makes the other side of the bond a partial positive. Okay? Add the symbology or annotate that on the bonds. Nothing gets annotated on the carbon because it's nonpolar. The fluorine-carbon bond, arrow points towards the negative, the partial negative of fluorine, and the positive slash towards the carbon. And then we need to take those and annotate them on the Lewis. I've got a carbon to fluorine pointing towards fluorine, another one, another, and another. And so fully annotated Lewis structure with the polar bonds labeled and identified has the arrows pointing from carbons to fluorines in all occurrences. Okay. Again, any questions? You see how it's important you have a really good Lewis structure before you start trying to do this, because if your Lewis structure has difficulty, it's going to be, I won't say it's going to be impossible, it's going to be difficult. Now for just a moment, we're going to talk about water. And this piece right here is a little bit out of order in my opinion. We'll see how it teaches and we'll go from there, but we've already talked about a water, and is this a Lewis structure or is this a Vesper diagram? It's Vesper. How do you know it's Vesper? It's not 90 degrees, right? It's offset. And so we can show the bent H2O molecule like this because it's in a plane, right? It has this one angle, and we recognize that these bonded or these unbonded pairs of electrons are not perfectly positioned like that, but that's the best we can do to represent them in a two-dimensional plane. This is actually a three-dimensional representation. Now, between hydrogen and oxygen, there is electronegativity difference, with oxygen having a higher electronegativity than hydrogen, meaning that the electrons are going to tend to be towards the oxygen, and as they tend towards the oxygen, they tend not to be at the hydrogen, which sets up the partial charges of the hydrogen sides being positive relative to the oxygens, right? They have the electron less, so they become positive, which means that the oxygens tend to have it more, and so the oxygens tend towards negative, or the oxygen tends towards negatives, and the hydrogens tend towards positives. Anybody feeling comfortable with this? Makes sense from what we've done today. Okay, so the electrons tend to be around the oxygens, they tend not to be around the hydrogens. The total charge of the whole molecule is a net neutral, but we can see from here that if we put a line through the molecule, that we end up with a positive side of the molecule and a negative side of the molecule, right? So even though the thing as a whole is neutral, it has a positive side and a negative side. And remember, neutral doesn't mean it doesn't have charges. Neutral means that its negatives balance its positives. So within the whole, it's balanced, but they're not perfectly mixed. It's not a homogeneous charge. It's actually a heterogeneous kind of charge. It's separated out with the negatives tending on one side and positives, or excuse me, positive tending on this side and negatives tending on this side. So we're actually going to do this lab. Now we're going to do it on Monday rather than today. But the original plan was this. Let's say that this right here, these positive and negative charges just represent electromagnetic forces. It'd be the same as having a positive and negative charge on a magnet and bringing another magnet into the area. If I had two electromagnetic fields and I had a negative side and it was corresponded to a positive side of something else, what would we expect to happen? They would attract one another. And that's actually what we see happens, is that this molecule is going to not only orient itself so that its positive side is towards the negative charge, but it's also going to move in space. It's going to move towards that negative charge. And we're going to do a lab on Monday that demonstrates this, okay? And we're going to actually have some liquid flowing and bring a charge next to it and watch the free-falling stream bend, because it's going to be impacted by the electromagnetic forces from outside itself. And it only happens because the fluid itself has a positive side and a negative side. If it doesn't have a nonpolar orientation, if it was symmetrical, it wouldn't have a net positive side and net negative side, and it wouldn't be influenced by these charges. But because, in this case, water does have a positive side and a negative side, it is influenced by the external field and does move. Okay? Let's see what we've got next here. Next we start getting into polar, nonpolar molecules. So actually that's our next discussion. What I'd like to do right here is go ahead and give you like a 5-minute break. Water fountain, bathroom, and then we'll pick up in about 5 minutes, okay? So take a break.